2:30, so we should get going. Most of the plan for today is to talk about torque. Before that, there's one other thing I want to say about moments of inertia, which will be very useful for us when we get to talking about torque. Okay. So, just as a reminder, remember we in the last lecture, maybe I talked about a wiener dog, right? And I talked about two different ways that it could rotate, right? So if it rotates around this point, that, the moment of inertia is 112 ml squared. This is L. M is the mass of this animal. And if for some reason it rotates around its, let's say, tail, okay, like this, the moment of inertia around an endpoint was that, and this came from like nasty integral calculations. Not that nasty, they could be worse. Anyway, we had to do a bunch of work to figure this out. And this is kind of painful, okay? So the point here is, on the one hand, it's just a fact that moment of inertia changes depending on which axis you use. And that means that you either have to calculate it fresh every single time, or you look it up somewhere, but that gets super annoying potentially, and it could take too much time. There's a better way of handling this change from one to the other, but it's got a very scary name. It's called the parallel axis theorem, and it's very easy to use. And I want to try to demystify it a little bit. So first it's going to look scary, and then as we actually use it, you'll see that it's secretly very, very easy to use. Okay? So the parallel axis theorem says the following. Imagine you have some object. That's the blue thing. Okay? And imagine it's got some center of mass. That's the dot over there. And suppose that you know the moment of inertia around the dashed axis, which goes through the center of mass. How do you know it? Well, option number one, you calculated it yourself. Option number two, somebody else that you trust told you what the moment of inertia is. You looked it up in some table, you asked a math major friend, you asked me, whoever, right? Somebody told you the answer. So now, suppose you want to know the moment of inertia around some different axis, let's say the red one. It's red thing. As long as this red thing is parallel to the initial axis that you were given, you can get the new moment of inertia by this formula. Okay? I won't show you the proof of this. It's not particularly hard, but we have limited time. I want to show you how to use this. And hopefully, as I do, you will see that it is simple. Okay, so there's a lot happening on this slide, so I'm going to do it slowly, okay? So what's the axis here? Axis of rotation. It's something that goes through the center of this dog, and the dog is chasing its tail. Okay, so it's rotating like this. And suppose what we want to know is the rotation, the moment of inertia around the end. So now the axis is coming out and going through the end of the dog. So this axis is parallel to that axis. So we're allowed to use the moment of inertia theorem, the parallel axis theorem. So what would that look like? It would say that the moment of inertia around the end of the dog is equal to the moment of inertia around the center plus the mass of the dog times r squared. Okay, so what is r? That's the key question here. So r is the distance between the center of mass, which is where we figured out, well, this thing, and the point that we actually are interested in, which is the end of the dog. right? The tip of the dog. And so, if this distance is from here to here, if this is L, so this is in the middle, the distance from here to there has got to be L over 2. So, what should happen is that the moment of inertia around the end is the moment of inertia around the center plus m L over 2 squared. So let's actually work it out and see what we get. This one is that. I mean, how do I know? Well, I have it on the board. I looked it up before class. That's what I had. So let's add in this other part. Right? 2 squared is 4. 2 times 2. Okay, so now we just have to suffer it through the arithmetic of putting these two things together and seeing what we get. So 1/12 plus 1/4 is 1/12 plus 3 times 4, because that makes 12. Look at that. So this, okay, math is hard. Let's see. Nope. Okay, so that's a third, and therefore, you see that it worked? Yes, go ahead.
Where does the 1/4 come
The 1/4, right. So this 1/4 came from this previous step where I had L over 2 for the value of R in the parallel access theorem. When I square the 2 downstairs, I get a 4 downstairs. Okay. Okay. Any questions about this? Could you do this yourselves if you had to? Suppose you didn't feel like doing integrals. You didn't know this answer, but I told you what this one was, and I asked you what is the inertia around this axis. You could use this to get the answer without ever doing an integral, which is an epic win, right? Who wants to do integrals? Nobody, not even me. So, okay. So let's actually use it to do something much harder, but you'll see that actually when you start doing it, it's still really easy, thanks to this magic theorem. Okay, so imagine I have these two spheres, these two balls, okay? So I'm gonna pretend like my fists are spherical, which is not a terrible approximation, and they're stuck together like this, okay? And now they're gonna rotate around the line that goes in between them, okay? So they're gonna do this. So now we want to know, what is the moment of inertia? Okay. So let's think about that. These are supposed to be identical. I know they don't look like it because I can't draw, but trust me, they are identical. Okay. So this is our axis, and we want to know the moment of inertia of this complicated shape. Now, this is a case where if you had to figure this out using calculus, you could, in principle, but this would be a devastatingly difficult problem on a Calculus 3 exam. Like, it would be really hard if nobody told you in that class about the parallel access theorem. And we're about to do it without ever doing an integral. I mean, this is the kind of thing that would make math majors cry. Okay, so, what do? So the first thing to do is to not panic and say to ourselves, okay, well, this is too complicated. Let me figure out the answer if I delete one of the spheres. Why is that okay? It's okay because whatever is going on, the answer is somehow like this, right? Just the sum. We're not actually going to do it, but the point of saying it this way is that you have to figure out what contribution you get from this sphere, and then add the contribution of that sphere, which means we can break up the problem into pieces and do each piece separately, then add the answers. It's much easier to try to do it at once. Okay, so the first thing we have to do, therefore, is we have to do an easier problem, which is, here's our sphere, okay? And we want to rotate it around the point that touches the edge. So that's now what we want to do, okay? So we want to do I of a sphere around the edge. Okay? Now that's still too hard, because I don't know how to do it. But now we can make up another problem for ourselves, which is a lot easier. What if we have a sphere, and instead of trying to do it along there, we try to do it along something that goes through its center of mass? And now we ask, what is the moment of inertia of a sphere around the center of mass? Now, this is a problem that a good Calculus 3 student, which none of you are supposed to be, could in principle do, but we won't do it. We're not going to do it, because you're not in Calc 3. So, that last thing is something that we just look up in a table or ask your instructor. And so, what do? You get a table of moments of inertia, you look at it, squint for a while, and you discover, okay, there's a solid sphere for rotations around an axis that goes through its center. I is 2/5 mr squared. All right, so let me record that. There we go. Now, this is totally not the problem we're trying to solve. But now we can relate this thing to that thing. How? This axis is parallel to that axis, so the magic parallel axis theorem is safe to use. So what does it tell us? It tells us that I for the sphere around the edge is equal to I for the sphere around the center of mass plus m distance squared. I'm writing it as distance squared, not as r squared, to avoid a possible confusion, so that you don't conflate things unnecessarily. So basically, we need to know what's the distance between this axis and that axis. So in this case, that distance happens to be r. If you had moved this in a little bit, it would have been different, but it really is just r. So d, in this case, happens to be r. It's just the radius. You all buy that? So this is 2/5 mr squared plus mr squared. So that's the same thing as 5/5. So this is 7/5 mr squared. Okay. And now, well, we got half the answer, right? So we just figured out the answer for the problem where you rotate around the edge. But that's for one of the spheres. Fine. So remember this statement, right? So you break everything up into pieces. So we just did half of what we needed to do. When we do the other half, it's the same exact argument, giving us the same exact answer. We got to add it to what we actually got. So I total, which is what we're actually looking for, is 2 times I for a sphere around its edge, which is 14. No, that's not, I write 14. 14/5 mr squared. And we're done. Now, again, if somebody gets this problem on a Calculus 3 midterm, I'm very sorry for you, but doing this using Calc 3 is very painful. But this evades all of that. Okay. I really hope that I got it right. At least it's consistent with what I did when I did it myself. Okay? So just to review, okay? We got this very complicated shape in some sense, right? Two balls stuck together, and now they rotate around some straight line going through the point where they touch, and we want to know the moment of inertia of this very complicated object. To figure it out, we break it up into two pieces, and we just think about one piece at a time. For that one piece at a time, it's still a hard problem because we're taking this sphere and rotating around some weird point, but we can relate that problem to a simpler problem where you rotate it around the center of mass. And for that problem, we can look at a table of moments of inertia and get the answer. And then we go backwards. We got this thing. We can use the parallel access theorem to get this, which is half the answer that we wanted. And then multiply by 2 to get the full answer. And we're done. Okay, so I wanted to show you this just because without the parallel access theorem, this would be a terrifying thing to try to do. With the parallel access theorem, I hope you find this fairly straightforward, at least with some practice. Do you have any questions about it? Yes?
Where's the 5 over 5? That's the R squared over there.
Say that one more time, please.
Where's the 5 over 5?
Where's the 5?
5 over 5.
5 over 5. Oh, okay, what happened with that? Okay, so basically what's going on here is what I got is actually this. I just replaced md squared with mr squared because d is equal to r. And now I want to write this in some simple form. So I gotta add these two things together. And this is 2/5. And I gotta add this part. So to add fractions, it's convenient to have everybody have the same denominator. And so what I'm doing is I'm rewriting 1 as 5 over 5. So I'm saying 2/5 plus 1, that's the thing that I want to figure out. Like, what is that? So I'm writing that as 2/5 plus 5 over 5, because that's 1. And then that is 7/5. So that's the trick that I'm doing. I'm going to figure out the coefficient in front of mr squared. Did that clarify it?
Yeah, thank you.
Good. Other questions? Okay, so this is like a rare case where something with a terrifying name of theorem is actually really useful. You don't even have to know why the theorem is true in this case. You can use it as long as it's for parallel axes. Okay, so enough about that. Let's talk about torque. That was not intended to be fun. Okay, so, man, there are various ways of doing this. But for example, okay, imagine somebody with a weird sense of humor ties a rocket to a string. Okay, and this end of the string is held fixed, and the rocket is constrained to fly in a circle. Okay? So the engine will apply a force in the direction of travel, so it will accelerate the rocket. So you could wonder how much work is being done on the rocket. Okay. So one of the things that is useful to note is, remember we had formulas like work is equal to force times displacement. This is a situation in which the motion is in a circle. So work is still work, okay? But now displacement is an angle. And so there should be some formula where force is replaced with some angular notion of force, okay? And that has the name torque. Okay? But so what is an expression for torque? That's really what we should try to figure out. All right. So the other thing that I think I've already said before is we have the standard formula F equals ma. So there should be an angular version of this where mass is replaced by moment of inertia, acceleration is replaced by angular acceleration, and F is replaced by tau, that's work. Well, if that's true, then work is I alpha theta, just by combining these formulas. Okay, and in fact, basically all the other formulas you used to have still go through. So for example, let me do this on the board, then you'll have it also in the slides, but maybe a slightly different order. Remember, work is change in kinetic energy, right? So kinetic energy itself is a half. You can either write it like that or like that, right? The second expression uses angular notions. So work should be the 1/2 I omega f squared minus a half I omega I squared. Just the difference between the initial and final kinetic energy. And we can put all this together. We take this thing, set it equal to that thing, we will get I alpha theta is equal to, these both have a half in them, and they both have an I in them, so I could write a half I so I set this equal to that. And now, there's something entertaining. The I's cancel. Yeah? And what we get is theta is equal to, oh, maybe I should write it somewhere else. So, if you have a good memory, this might look really eerie, because it's just the same formula as we had before for like distance is equal to final velocity squared minus initial velocity squared divided by twice the acceleration for motion with a constant acceleration. You remember that? It's just renaming everything to their angular versions. So these are meant to be analogs of each other. Do you see that? They're just the same. But one of them is useful when you have things that are rotating. The other thing that's useful when these things are just moving in a line. Okay, so that's our first taste of this kind of reasoning. These slides that I'm going to go past relatively quickly are just intended to say just like exactly the same thing. So there we go. It's the same final punchline. I just said it differently on the board. Any questions? So, we have a dictionary for every linear quantity that's basically an angular quantity. Torque is just the new entry that we're talking about today. Now, the question that I want to ask is the following. I'm going to say it slightly differently than it's on the slide, although it's basically the same. So we have a relationship between standard linear notions of velocities and accelerations and angular versions of those things. And we have a relationship between moment of inertia, so it's more complicated, but moment of inertia is related to mass and position by some complicated formula. Okay, but there is a relationship between just standard things which are about masses and locations and these angular quantities. So the question now is, what is the relationship between torque and the more familiar by now concepts like force? Right? So we have torque on the one hand, and the question is, how is it related to things like force and position and so on? So like, what's the formula? So that's what I want to try to understand and show you what the answer is. there are many ways to think about this. I'm going to try to see if I can give you two different ways, make sure that it's clear. Let's start with the one that's on the slides. Okay. So imagine that this rocket has only moved a little bit. Okay, so D is very small, so it started horizontal like this, and it moved up a little bit. And the hypotenuse is R, and the angle theta is very small. In that case, D over there, which is basically just R sine theta, for small angles, sine theta is very close to theta. So D is approximately R times theta when theta is small. So far it's not clear like why is this interesting. But the punchline is that if you believe that, I'll rewrite it here. If you believe that work is force times displacement, and here the displacement is D, okay, then, well, if you're okay with the statement that displacement is approximately R times theta, then at least for small theta, this is F R theta, for small theta. And it makes it at least a little bit plausible. It motivates a guess, okay? So the guess could be, well, maybe the work would be something like actually, let me not do the guess. I'm about to lead you wrong. I'm sorry. Leave that idea. Okay. So the point of what I just wrote, FR theta, for the work is that it suggests that if you want to write work as some kind of torque times theta, then the torque looks like it's F times R, at least for small theta. Okay. So that's our initial expression for the relationship between torque and forces and where you apply the torque. Okay. You can add torques. I want to come back to this. Just bear with me. Okay, so what I want to do first is the following. I'm going to deviate slightly from what I have on the slides, because I think that there's a nicer way to explain this. Okay, imagine I have a stick and I have an axis indicated by the black dot. If I push on the stick like that, it's going to rotate, right? This will cause rotation. If I instead take the same stick and I push down like this, well, one possibility is the whole thing will just move down, right? But if I really nail down this axis and it can't move, it can only rotate around this axis, then literally nothing will happen, right? This will cause no rotation. And if torque should somehow measure, like, if applying a force should produce a torque, and torque should make things want to rotate, which it ought to, just like applying a force to something makes it move, then the torque in this situation should be zero, because it's not going to cause any rotation, and the torque in this situation should be non-zero. So this is non-zero torque. And this is zero torque. So again, the reason for these statements is that torque should make things want to rotate. I'm trying to understand the relationship between forces and torques. And in this case, applying this force should cause a rotation, but so there should be some non-zero torque. In this case, applying the force should not cause any rotation, so the torque should be zero. So now let's think about it a little bit more generally. Let's say that we have this stick, and we, instead of applying a force directly from the side, let's apply it like that. So now we want to ask, does the thing rotate? Well, so the answer is yeah, of course it's going to rotate, but let's think about it more carefully. This force, part of it just pushes in, right? Like some part of this force just pushes in on this stick. And that part of it is not going to contribute to rotation, because it's just like this. And there's another part of it that pushes that way. This part is the useful part. It's the part which actually makes the stick rotate. One way of referring to this part is the tangential part. Why is it tangential? It's because if I draw how the thing will rotate, it's the part that's along the tangent. You see that? It's like along the tangent to the circle that the end of is going to execute. Okay, so what it means is it's very useful for us to figure out what is the what is this part of it. So okay, so to do that, it's very useful to introduce some angles to this game. So let's say that this vector is r, the one from here to here. Okay? So, let's say that this angle is theta, just for the sake of argument. So I'm saying that this angle is theta. So if you do a little bit of trigonometry, you'll see that this angle is also theta. I don't know if you believe me. This angle right here is 90 minus theta, and this angle is 90 degrees. So to make sure that the angles all add up to 180, the angle in the top corner has got to be theta. Okay. So now we have a triangle. We want to know what is that side, and we have this angle theta, this is the right angle, and this side has a size f. We want to know how big is this side. So the side in question is f sine theta, from the trigonometry that we've seen before. So what does that mean? So this is the part of the force that is useful. This is the useful part of the force. Another way to say it, this is the tangential force. Okay? Torque only cares about that part of the force. It doesn't care about this force. This is the radial force, because it pushes in the direction of the radius. That force does not produce rotations. Torque doesn't care about it. So what do we get out of this? The torque should depend on the tangential force. The bigger that is, the bigger the torque should be. And the other thing that matters is how far away from the axis you push. And it turns out that the right answer is this. So R is how far away from the axis you push. And that's the dictionary entry we're after. Any questions about that? Okay. So in the slides, there's like a more complicated way of getting to something similar. So let me not do that. So instead, I want to motivate a Tryman. So bear with me. So in some ancient TV shows that may or may not still be on the internet, there are creatures called hobbits who, for presumably architectural reasons, like to make doors that are circular. That's the first weird thing. And the second really weird thing is they stick handles in the middle of the doors. This definitely looks nice. It's very symmetrical. Okay? It kind of looks like a screaming mouth. So I don't know if that's kind of terrifying now that I think about it. Okay, but let's bring this into physics. Why don't we do this? Okay, so I'm going to open the question. Okay? So why don't humans make doors like this? It's definitely symmetrical. So your choices are A, humans don't like symmetry. B, you get more torque from putting the handle in the center. So hobbit doors are easier to open. And humans are very strong, so we're happy to work harder. And by the way, I mean, if you think about how this door is going to open, it sort of doesn't matter where you put the axis of rotation, whether it's on the, it's got to be on the edge, right? So it's either the top or the bottom or the sides. Pick your favorite. So like, the question is this a good place to put the door handle? Okay. I'm very curious what your intuition says. Okay, thank goodness. Okay, so this is too easy. That's good. That's good. Too easy is good. Okay, so like, I mean, we don't do this because we know about physics, right? So now the question is, that's not a Feynman question. It's like, why did people who make TV shows about magical creatures sometimes make these kinds of doors? Well, I don't know. Maybe hobbits are not that smart. That's one possibility that the TV makers are saying. It's possible that some of the artists that design doors for TV and movies don't take physics classes. It's possible. And the final answer, I think, is actually correct. Is that, I mean, the artists probably know this is a silly thing to do, but it looks cool. That's the important thing. So they went with it. All right. Just to drive it home, if you have a door, I'm not completely sure what this part is. If you push on the door straight into the board, right there, with a force F, straight in. This is the hinge. The torque will be your force times the sine of the angle between your force and this radius vector. But if you're pushing straight in, this angle is 90 degrees. Keep that in mind. And now let's say that the length of the door is L. So it's going to be L over 2. Okay, sine of 90 degrees is 1. So this is F L over 2. So this is the center torque for a door handle at the center. Okay, if we do F, right, tau of the end of the door, right here. Okay, so suppose you push straight on the door right there, same argument, F sine theta, or this is 90 degrees, times L. So you get twice as much torque. So for the same amount of force, you get twice as much turning action. That's nice. By the way, I have some experimental evidence that like appreciating these facts takes time. I have a 5-year-old who doesn't get this yet. Every day we go through like which part of the door should you press on, and he really likes doing like here. So yeah, anyway, so probably all of you know that it's like not a good idea to try to open the door by pushing next to the hinge. So that comes with experience. Okay, but if you knew physics at 5 years old, you would know by doing a quick calculation that this is obviously the best way to get some turning action. Okay. Okay. So, do you have any questions before I continue?
Are we gonna study like fourth north points and what it means at all?
Yes. The question was, sorry, just for everybody, are we going to study about like torque as a vector, because it is. So, yes. In fact, momentarily, if I remember correctly. Because somewhere on the board, I guess that's not that clear in any one equation, so bear with me for a second, because I've made a bit of a mess. We have that the torque is equal to the force times some distance times some sine of some angle. And if you stare at this long enough, and for some reason you remember some lecture, like a month ago, or maybe 2 months ago, where we had various kinds of products, dot products and whatever, we also had a vector product. And this is secretly the vector product, okay? So torque as a vector is the radius as a vector crossed with the force as a vector. Okay, but that is unlikely to be illuminating without more comments. So let me try to make those comments. But before I do, this should be slightly terrifying because dot cross products are slightly terrifying. Okay, so I went somewhere else with this after this slide. Sorry, what was I doing after this? 1 second. I don't want to just write this equation and just leave it there. Okay, so let me just explain. Okay, so what does this mean? So what this means is the following: the magnitude of the torque vector is that Fr sine theta. And the direction that it points is slightly complicated. So let me explain how to get it. Step 1, use your right hand. Okay? So, okay. This is always really bad, okay. Okay, so then 2. Point index finger in direction of R, and then thumb in the F direction. Okay, and then, okay, so this is like a preparation. Okay, it's gonna hurt, I'm sorry, or hopefully not, if you have the right dexterity. And then, okay, I'm just writing it, and then, so what you do, okay, is you take your pointer finger, you point it in the direction of the first vector, R. You take your thumb and point it in the direction of the second vector. And then your other fingers, if you have standard human mobility, point in some direction that's relative to those. But please don't bend them back by like this, okay? Just like let them do something natural. They're gonna point in the direction of the cross product. So let's see if I can do it here. Oh man. So the first thing I'm gonna do is, with this door, right, the radius vector, I gotta draw it. See, the radius vector is from the axis to the point where the force is being applied. So, like that. And then my, oh no. Can I do this? something seems terribly wrong. Okay, so the force is, no wait. Yeah, the force is in, and so I'm getting the torque is down. This is my right hand.
You use your index and then your thumb and then your middle finger, but you're supposed to use thumb, index.
Oh no, thank you. Wait, say that again. So something went terribly wrong, so I must have done it wrong. Say that one more time.
Right hand goes thumb, index, and index, thumb.
Oh, well, that'll do it. Okay, it's been a day. Let me try to do it the correct way because clearly that was like, basically, okay, let me just put cards on the table. The torque should go in the direction of rotation, okay? The door, you better hope, is not gonna rotate down that way when you push on it. That means the hinge broke. So you're right. At least I hope. Okay, so let me see if I can get it straight. So, point the index finger is in the direction of the thumb goes in the direction of the first vector. Is that right? So thumb finger. Thank you. And then your, this is terrible. Your pointer finger goes in the second direction. Thank you. By the way, sorry, is this called the pointer finger or the index finger? Both? What is wrong with English? Pointer finger. I'm going to go with pointer finger. Okay, and then your other fingers go in the correct direction, hopefully. Wait, let's see. I feel like we're about to go into trouble, which means I'll have to revisit this at the next lecture or over email. So let's try it one more time. Okay, so thumb is going to go in the direction of the, oh no. So thumb is going to go in the direction of the force. Pointer finger is in the direction of the, sorry. Thumb is in the direction of the radius. Pointer finger is in the direction of the force. My other fingers are now pointing up. If the door goes up when I do this, it's also not good.
No, that is right.
That is right. Oh, sorry. The torque is up because the direction of the, yes, it's correct, It's correct, right? Yes, it's correct. Sorry, it's correct. So when you have a motion like that, the torque is actually up. Yes, that's right. Vectors are so annoying. I'm sorry. This is, believe it or not, I've done this class like 3 times. This is my first time completely screwing up this explanation, so I don't know what's wrong. Okay. I'll have to do this again clean at the beginning of the next lecture, so don't run away. We're almost there. Okay, so this space was correct. Let me make sure there's nothing like super important you need for the homework. The answer is no. Okay, so then I think it's safe to run away. I'm so sorry for screwing